Hi, welcome to the presentation of post-training quantization for super resolution. I'm Zhijun Tu. This work was done by me and my colleagues at Huawei Noah's Ark Lab. This paper studies the post-training quantization for image super resolution with a few unlabeled calibration images, which could help the faster deployment on mobile devices. Our analysis indicates that the long-tailed asymmetric distributions and highly dynamic ranges of activation greatly degrade the performance of quantizer models. To address that, we propose a close-to-5 post-training quantization framework for super resolution. With the density-based dual clipping, we could get the initial lower and upper bounds of asymmetric activations for super resolution models and cut off outliers, and then fine-grade optimize them with the novel pixel-aware calibration method with the supervision of the full precision models accommodate the highly dynamic range of different samples. Extensive experiments demonstrate that the proposed method could significantly outperform existing PDQ algorithms on various models and datasets, and we also shows that our method could provide a better initialization for QAT. The ablation studies further prove that DCDB and PAC could help improve the performance of post-training quantization for image super resolution. This work studies the model quantization for image super resolution. Model quantization is the crucial step for deploying networks on mobile devices. Although the previous SR quantization methods make great effort on improving the performance with given bitwise, their main drawback is that they require quantization-aware training with complete datasets and expensive computational overhead as shown in this table. On the contrast, post-training quantization only requires a few unlabeled calibration images without training, which enables faster deployment on various devices within minutes. Different from the image classification, super resolution requires accurate prediction for each pixel of the output images, which is much sensitive to low bit compression for future maps. As shown in this table, when we only quantize the width to 6 bit, there is only a little performance drop. On the contrast, when we only quantize the activations, the result on decreases much severely, which indicates that the quantization on activations greatly degrade the performance of low-bit precision models. Then we further visualize the activation distribution of immediate layers and conclude 3 properties that are harmful to quantization. The first is long-tailed. The distribution shows to be dense in the middle and sparse in the tails. Most of values lie in a small range, while only a few outliers have larger amplitude. The second is asymmetric. The density on the two tails of the distribution is asymmetric. The third is highly dynamic. The activation range varies or even by twice for different input samples. Therefore, the existing post-PDQ method, which are designed for image classification, cannot be transferred to the SR task directly. To address above issues, we propose a close-to-5 method to get the accurate quantizer SR model with post-training quantization. The first step is the density-based dual clipping aims to cut off most of the outliers for narrowing the distribution to a valid range. The second step is the novel pixel-aware calibration, help the quantizer network fit the highly dynamic activation for different samples. Firstly, we briefly introduce what is the model quantization. There are 3 steps in tensor quantization. Truncate the original tensor into a fixed range, then map the floating point tensor to the integer tensor. Finally, reconstruct the floating point tensor from the integer tensor. The post-training quantization aims to get the optimal clipping values of widths and activations for all the layers without the modification to original widths. Then we introduce our method in detail. For density-based dual clipping, we first divide the origin activation into the unequal interval based on its min-max value. By comparing the density value between the position of lower bound and upper bound iteratively, we make the clipping position with smaller density close to the middle. Finally, the global bounds are updated by the exponential moving average method. With the DBDC, we can cut off outliers of activations help narrow the distribution to a valid range. Then for pixel-aware calibration, with the unlabeled calibration image and the full precedent pre-trained model, we can build a dataset for fine-tuning, and then we construct the PAC loss between the output and the feature maps of middle layer for full precedent model and the quantizer model. To stabilize the fine-tune process, we further propose to iteratively optimize the clipping parameters of weights and activations instead of fine-tuning them together. This is our experimental result of EDSR. Our method obtains the best performance on various bitwise settings. And this is our experimental result of SRSNet. Our method also obtains state-of-the-art result compared with the existing methods. And we also combine our method with the quantizer-aware training. As we can see in this table, our method truly improves the performance. Besides, PTQ4SR can speed up the convergence of QAT process. These are ablation studies and visualization results, which show the effectiveness of our method. So, well, thanks for watching this presentation. We open source our code in this two link. If you find PTQ4SR is interesting, you could use our code to conduct experiments. Thanks again.